Okay guys, so we're continuing the designing observer and started in the previous class. We are done by designing the control signal for the LTI system, and I told you that the observer means simply means what? Means estimating what is this? Estimating, we change the color. Oh, state variables. That's right. Estimating state variables where, for example, we have no reliable sensor to measure it, or sensor has noise, sensor is affected by noise, or state variable is not accessible to be measured. Okay, so we are estimating state variables. So when I say observer, it means that we are estimating state variables. In the previous class, I talked about if you estimate n state variable, that is the order of the system, you have full order. Remember from previous class? Full order observer. If you estimate fewer than n state, its name is reduced order observer. Okay. And I said in the previous class, we measure or estimate state variables based on the measurements of the output signal, that is y, you know that from this x dot is equal to ax plus bu, and the y output is cx, remember, for the LTI system, and control signal, which is what? This is u. So we are measuring based on this and this. So we are estimating state variables. So this is very important, guys. Now, if I want to write a mathematical estimate of this to go to designing observer, so let's go to mathematics. Then, like at the control design, I'm gonna develop the MATLAB code and you're gonna enjoy it. Okay. First of all, this is your state variable, but when I say it's not unmeasurable or sensor is not accurate, so we're gonna say x bar, that's right, x hat. So this means that we are estimating. This is unknown. We are estimating unknown. Well, so when I say that, this is unknown. So this we name it as the observed or estimated. This is how we name observed or estimated state vector. So okay, observed or estimated, estimated. This is notation for that. So now this is the system, LTI system, that we designed controller together. That's right. In theory by Ackermann or other methods, and in the MATLAB. Y is equal to Cx. Now we have to know some definitions. Observation error. It is difference between estimated output. I'm changing the color, gonna be y bar hat, which is equal to c x hat, estimated output, and measured output, real that we are measured. This is what? This is measured output is y. This is y hat, this is y. So the observation error is y minus c x hat. So because y is cx, it's going to be x minus x hat. That's right, this is observation error. Another term that you have to know in designing observer or estimator of the state variables is initial error. Is difference between the initial state and initial estimated state, mathematically talking. So because you have initial state, so this is your state vector, initial at time 0, or let me say at not 0, at t naught, at initial value. T can be anything. So here this is initial estimated, so this is estimated, that's right, at time 0. This is the initial error, and this is observation error. Understand? Now what we are doing in the observation or estimation of the state variable, this is simply like that. Look at here, because here I said we measure state variables based on measurements of the y and u. Now I'm gonna write it mathematically. We're gonna say in observer, okay, x hat dot, because we don't know, we are estimating, is a x hat because it's estimating unknown, plus bu plus ke, this is gain of estimation, in observation error that we just defined here. This is what? This is observation error, that's right, observation error signal. Here we go. Understand? So if you rewrite that, because you have x hat, so you're gonna have a minus c ke in x hat plus bu plus ke y. Now this is exactly what we said. Now we are writing in mathematics. We are measuring or estimating the state variable by the output, measured output y, and control signal. That's right. But this is familiar to you guys. This is a very familiar term. Why? Because when we were designing the controller U signal, we came up with the A minus bk, remember, minus bk, that's right. So, and this is the gain that we did with the Ackermann. So we have another gain that we have to again determine, understand? So here x hat again is estimated state, means state variable, and the cx hat is estimated output. Understand? So for estimation, means estimation, the input to the system is what? Output and the control signal. So hence, again, I'm just writing hence input to the observer are output, measured output y, and control input that we designed together in previous classes, u. Understand? Now, as I said, this is a gain that you have to now again tune it. I'm gonna show, like, very similar to K that we did for control signal. Okay, so KE, so KE is oh, it's warming up, hold on guys, is called, let me change the color, observer gain. The name of the K, observer gain, observer gain, that you have to do that. Now if I want to plot the block diagram of this, that exactly you see here guys, AX plus BU plus KE y minus CX estimated. If I want to plot the block diagram of this as I did for the control design, U comes inside control signal. One branch goes to being multiplied by B here, B, right? So this B obviously is being summed as you have summed previously in this class. Gives you x dot, but the x dot you have to have an integrator to give you x. This x is being multiplied, if it is known, by a, right? A, God, hold on, that this is warming up, I have to fix it. Okay, hopefully now this works. Okay, so if that a being summed, ax plus bu is x dot, so this if x is multiplied by c, gonna be y, because y is equal to cx, remember? But we are using this y here, so one branch of the y goes to here because we are estimating. Now the other branch goes here again, is being multiplied by b. Now I'm writing this equation. I just want to get y for this equation, is b. So b again goes and goes being summed again, that's right. So bu, that's right. Plus this term, I want to just generate this term. So you see that bu, this term must be, see, it's very easy, ke, observer gain, right? but the ke multiplied by y minus cx. So you see that I have some operation here. That's right. So y is coming plus and minus cx. Here is minus. This is gonna give such term. So the other side of this is y. See, y minus cx. So here is minus cx. But cx, we know that, as I told you, is estimated output. So here is y hat. Y hat. That's right. Right? Why is he not writing again? Right? So y hat is what? As I said, is cx. So here's c. So here you have what? Here you have, this is your x hat estimated. Cx is a y hat. Y hat minus y multiplied k discuss. So we got until this point. Understand? So, but obviously we have x hat dot. So we need the integrator here, like this part. Here's integrator, and now goes this. So this is x hat bar. X hat bar, as you see here, x hat dot is bu plus. So plus ax. So here you have to have. Sorry guys. You have to have another thing. Plus. This is your x hat bar. X hat bar is bu, so bu plus ax. That's right. So ax. So this is x hat multiplied by a. Here we go. X hat bar is bu plus ax, and then after integrating give you x bar multiplied by c y bar, and y bar minus y gives you this. So now we have the loop. So this part of the block diagram, obviously, this part of the block diagram, this part is what? Is observer. I don't know what happened. Sometimes it's become crazy. It is observer. Observer, as you see. So this part is this equation. Here we go. Now let us go slowly toward its designing observer, and then after developing this mathematical formulation, I'm going to transfer it to the MATLAB along with the designing controller. You see that a control problem is two parts. One of them designing the control input U, another is that you design observer to estimate unmeasured state variables. Has two separate components that can be integrated into one problem I'm going to teach you. So here, let's go on eventually design. So full state observer or estimator. Observer. For this full state, as I told previously, the order of the state observer is the same as that of the plant. If the plant has nth order system and you have n state variable, so the order of the state observer is n, because you're estimating all of them. Understand? So if you write x dot is equal to ax plus bu, plus bu, why is plus bu, hold on, okay, bu, and now you say, you know what, I cannot measure it, so let us do by observer. So you're gonna say x hat dot is a x hat that we don't know, we are estimating, plus bu plus, as I said previously, this is the weighting term, y minus cx hat, but y we know is cx, equation number 1, equation number 2. If I subtract 2 from 1, it yields x hat minus x dot minus x hat dot is equal to ax minus ax hat. This, but this goes to hell, minus ke cx minus cx hat. That's right. So obviously, if you rewrite this, you're gonna have this. You're gonna have see, a x minus x hat minus ke, that's right, c x minus x hat. You can't factor out c, so you can write finally like this. This is equal to a minus ke, oh my god, kec x minus, I don't know what's happening today, x bar. Yes or no? Yes or no? Yes, that's right. Now I define, let me change the color. Now I define x minus x hat, means difference between the real state variable and estimated as e, as error signal between them. So you can write this equation as this: e dot is equal to a minus kec in e. Is it familiar to you? Yes, because when we were designing the control input, we had this e dot was a minus bk, remember, in e. So you see that there is a great similarity between defining the gain matrix for the k and the gain matrix for the observer. So what already have done for the control design, if we do that for the observer, fine. It says that even when you go to the MATLAB code after graduation, you again for design for KE you have to use Ackermann formula. Oh yes, I'm going to teach mathematics first. In the final exam you have to do the same along with the MATLAB, not only MATLAB. Okay, so if matrix A minus KEC is a stable matrix, means its eigenvalues are negative, that's right, E will converge to origin as we did for the ordinary differential equation, meaning that x hat of t, estimated x, will converge to x. Why? Because we said E is x minus x hat. So if that goes to 0, means that x goes to x hat, almost. That's right. So if the plant, any plant, robotic system, electromechanical system, your car, whatever, is completely observable, it can be proved that it is possible to choose metrics KE, such that A minus KEC has arbitrarily, I'm changing this because you have seen the control design, desired what? Come on, eigenvalues or poles, eigenvalues. See, so they did the same problem, only we changed A minus BK to A minus KEC. We just switched the place of B with C matrix. So, conclusion is, designing a full order observer becomes that of determining the observer gain matrix KE, in that ET, error signal between the real state variable and estimated state variable. In that ET is asymptotically stable. Here we go. So you see that it's the same problem. Recording? Yeah, it's the same problem of designing controller. So again, simply designing the observer is again what? I'm just putting on several star. It is again a pole placement problem. But again, if we are going to use mathematics, if I tell you, okay, what kind of the poles that you want to estimate your state variables, you never give, so what's your option? Is under-damped poles or the critically damped poles? Depends on the system that you want to design controllers. Sometimes if you estimate the state variable, that is temperature of the room, as under damp estimation, so your system gonna feel temperature of 100 Fahrenheit. Do you like it? You are designer, okay? So how we do that? The things that you have to learn, this is super important, guys, super important. In the mathematics we have a principle that we name as duality. Means two problems are mathematically the same is called, this is very important, guys, duality. So, okay, and we do have two problems. One of them is designing the control input, control signal, controller, U, and other is designing the observers. They are the same problem, because one is dealing with the A minus BK that we did together, gain matrix to follow zero non-zero reference input, and other is A minus KEC, right? Which is observer gain. We have to define it. So they are the same problem. That's why we name it duality for this effort. So what is that? Okay, hold on. Okay, now it's working. Okay, so remember in the control design we had a method of direct method. That's right. What was that? Remember? Let me go with the notes. So the first that you have to design your KE is a direct method. And direct method, that if you remember that I was teaching, was for the order of the system smaller than or equal to 1. That is feasible to do that by your hand. Remember that for the controller design I had this, because I said this is the characteristic equation of the system. Remember, A minus BK. If you go to your notes, this is the characteristic equation, or the denominator of the transfer function. So I said that if you want to have these are, what is this? Okay, so if you want to have desirable eigenvalues of the poles, that the denominator, so for the nth order system was this, remembered? Go to your notes. This is for designing U, which has minus kx, and we were defining k, and we put here, that's right, and we put here for the state feedback. Now the same problem is here, only the difference is that it's KEC. So as I said, you have the same problem. You have to use this SI minus, because of duality, A minus KEC. Now you have the desirable eigenvalues of the poles for the observers, right? So you're gonna have S minus mu1 again for observer, S minus mu2, that's right, mu2, and multiply by for nth order system S minus mu1, because you have n state variable to be estimated, understand? But here because it's order 3, where n is smaller than 3, understand? So let me go by example and see that what we have done exactly for the control design we are doing with the observer. So this is the example that I'm doing first. Now here in the next class on the MATLAB coding. So the example is this example for the system x dot is equal to ax plus bu, and the y is cx, means this is LTI system, where a matrix is 0, 20.610, and the b is 0 and 1, and the c matrix is 1 and 0. This means that only I want to see x1, because your x is second order system. So I want to just only see x1 because y is equal to cx. See here, 1 0 in x1 x2. So it's gonna be only x1. I just want to see this x1. For this system, we want the hold on. Okay, so please, we want the desired eigenvalues of observer matrix B mu1 is -10 and the mu2 is minus, because we have second order system, so we have two state variable to be estimated. So now design the observer, meaning that determine observer gain. Okay, but before that, let us discuss this. Why we want to have observer has two poles eigenvalues, that they are negative obviously must be, and why -10? Because if these are the poles, they're gonna vanish so fast, so you can observe or estimate your state variables as fast as you can. Understand? So, but if you make them a complex conjugate poles, it's gonna oscillate estimation of your state variable, like as the control design problem. So you have to be very cautious when you are you have desired eigenvalues for the observer. So first, that you as a contrologist, you have to say, you have to check if, as I taught you, your system is observable or not. How was that? I taught you, yeah, observability matrix CA. Remember this matrix, rank of this matrix. Obviously, C is 1 0. CA you have to multiply by that. Get here, 1 0 multiplied by what? 0, 20.6, 1 and a 0. 0 0. Sorry. Oh, I wrote. Oh. Say a problem is here is discussed. Okay, it doesn't care. It doesn't matter. So let me see this, because it's gonna make it difficult. This is 0 1. You wanna output is x2, because if I put 1 0, it's gonna be a singular matrix. So, and here is your C is this by original. So 1. So your C is that 0 1. So 1 and what? 1 and 0. So rank of this matrix obviously is 2, because the determinant is non-singular, that's right? So your system is observable. First we have to check it, guys. Maybe you design the observer, at the end you see that you cannot reach the answer because your system is not observable. Okay? Now, as I said, that because E dot is equal to A minus KECE, that's right, and I said that SI minus A minus KEC equal to S minus mu1. Mu1 is 10 plus 10, that's right, huh? Another is S plus 10, that's right. These are the desirable eigenvalues that you want to have for the observer. So now let's do that. SI is second order system, gonna be S 0, 0, S A minus KEC. So your A is 20.610 minus KEC. Your KE, it's what? Your KE, it is KE1 because you have 2. KE2 must be KE1, KE2. Right? In C, your C is 0 and 1. Right? This is 2 by 1. This is 1 by 2. The result gonna be 2 by 2. So again, this is gonna be, I'm subtracting this one, it is S minus 20.6 minus 1 and S. Now this is 2. 0 KE2, that's right. 0 so 0 KE1, I say KE2, and 0 KE2, that's right, 0 and KE2. So this comes determinant of, finally, S minus 20.6, right? And because this is in minus, this is going to be plus. S minus plus KE1. So minus 1 S plus KE2. Determinant of this simply is S in S plus KE2 and plus KE1 minus 20.6, right? It's gonna be S square plus KE2S plus KE1 minus 20.6, but the other side is this. This is S square plus 20S plus 100. So this is gonna be equal to S square plus 20S plus 100 plus 100, right? Come on, 100. Hold on, guys.